今天我们继续把 transmission line 的部分呢，做相当程度的介绍。那很快的，大概在2个小时，我们可以把这一章结束掉。那所以开学差不多，你们应该很习惯开学了，right？所以我们来看一下这个 transmission line， 一些重要的概念。你会发现我没有把那个 decay chain 里头的所有的细节跟你介绍。我上课基本上会比较重视观念的部分，那一些这个计算的细节还是要请各位自己回去做练习，好不好？Well, last time I told you that the transmission line, you need to put some application in the end of it, right? At the end of the transmission line, you attach some application, and very often that you put the antenna or put some whatever application you wish to do. So with the some application in the end, then you add one more boundary conditions to calculate the unknown parameters. Well, basically, if you put the low resistance here, low impedance here, then there must be some voltage across it. 有一个这个电压在这上头。Well, definitely you can measure some low current across this device. So this will allow you to relate the low voltage and low current with a ratio equal to the low impedance. Okay, so you have sort of 3 variables in these 2 equations. So you can sort of figure out 2 unknown variables subject to an unknown variable. Okay, so suppose that this is unknown to you, this is unknown to you, then you can express VL and V naught minus in terms of V naught plus. So you only have one unknown left from these 2 equations. Okay, so at the most you can only calculate the ratio between these 2 variables because this is still unknown to you. 在这个式子里头呢，你所不知道的这个值你还是不知道，所以你顶多只能算出一个这个 ratio 出来，它们之间的比值可以算得出来 ，OK？ 但是这个比值很重要 ，basically it tells you that how much voltage or how much current is reflected back to the generator, and to have a high energy deliver efficiency, you want to have small reflection coefficient. Okay, so this is a quite important parameter you have to consider in practical design. And this reflection coefficient is always less than 1. Okay, it's not going to be over 1 because whatever you put in is not going to get amplified back for passive elements. 它是一个 passive element， 所以反射的这个值呢，绝对不可能比这个送进去的值还要多。OK， 那another thing is that I told you that for transmission line, the phase is quite important. So in general, this gamma has a phase. It's a complex number. Okay, and this will tell you which location you're going to get a large value of reflection and which location will give you a small value of reflection. So once you have reflection, you establish a standing wave on the line. Okay, for complete reflection, then you're going to have complete cancellation at a certain point. But if you have partial reflection, then the cancellation for destructive interference is not going to be complete. 如果说你反射的波的这个强度呢不是100%的话呢，那你的这个破坏性干涉不会掉到0的地方去。Okay, so for partial reflection, the standing wave pattern is going to look like this. So there's certain maxima and also there's certain minima on this line. And from this original solution from the telegrapher from the transmission line equation, you can tell which location gives you the maximum value of voltage or which location gives you the maximum value of current. Okay, 所以呢，我们把它放进来，假设它是 lossless, therefore there's no alpha in this expression. Okay, so this is just an approximation for good transmission line with very low loss. So alpha is 0, okay? And then you put in the gamma value into this expression. You notice that initially you have V naught plus and V naught minus, 2 variables. Now you only have 1 variable, 1 unknown in this expression. Okay, 因为最后的这个边界条件给你的这个把这个v0负这个参数呢，把你算出来的，然后呢，定义了一个 reflection coefficient 在里头。所以在这式子里头 ，you only have 1 variable, okay? So you can sort of calculate the maximum value of this subject to this term, and if you reorganize it, you pull out the propagation term to outside, to outside this parenthesis. Then you can tell right away that this is the positive value. So if this value is multiple integer of 2 pi, then you maximize this term. Therefore, you have a maximum v. Well, same thing. If you look at this expression, this is if this is a multiple integer of 2 pi, 0, 2 pi, 4 pi, 6 pi 等等. Then you have a minimum value of I. So when you have a maximum value of V, you have a minimum value of I. And that is because the power propagating on this line is conserved, right? So when V is large, I has to go down. Therefore, V multiplied with I is a constant value. Okay. So this is because of the energy conservation, power conservation. Okay. So just following the discussion a while ago, you can actually calculate the location of the line, location of the maxima and minima on the line, on the transmission line. And I want to remind you that the definition of Z is equal to 0 at the end of the line. You could put some, say, some antenna here or have some low resistance right here, okay? At this point, is Z equal to 0. And whatever before this line, Z is a negative number, okay? Z is a negative value. Therefore, we put minus sign right here instead of plus sign, and n is a positive integer, okay? 所以这为什么这里会有个负号，就是因为这个 z 呢，在我们的这个式子里头是以负的值来表示。Okay, so and you have to get used to it. Okay, good. So with this multiple integer of 2 pi, you have maximum value of v and minimum value of I. Okay, 那同样的，你如果让这里变成负的话呢，这里变成派3派负派、负3派、负5派、负7派等等，这里就变成负的，你这个值就变成最小值。Okay, so if you set this condition, the R multiple of pi will give you the Z location along this line that your voltage is minimum and current is maximum. Okay, this is how you determine the location where you find the maximum value of your signal or minimum value of your signal. Okay. 那这里呢，我特别提醒你一下，就是你可能会觉得为什么这里呢最高值电压最高，电流就必须最低？ Well， 因为在这上头呢，你在这上头 propagate 的这个power 是 fixed， 所以 power 的话是电压乘上电流，所以你会有一个这个 inverse relationship 在那个地方。那in a few pages I'm going to tell you how to calculate the power. Okay. Any question? 有没有任何问题？我应该跟你们有多一点互动哈，所以呢，我今天download了一下你们的这个名单，所以呢，我可以开始认识你们。So, I think this is the one. 王伟成，你好，听得懂吗？有问题要问 ，OK， 没什么可怕的。 我们实验室，我上回好像提到，我们实验室这个每个礼拜会有这种学生来问问题，通常都是这个年纪越小的问题越多，然后一直到了大学之后，大家就不问问题了。这个一定跟老师这个跟老师有关，哎，所以有问题就问。So let me go back to this. Now, once you have reflection coefficient, you can sort of find a way to describe the standing wave. Well, apparently, the standing wave, well, this is the standing wave pattern. This kind of standing wave is going to be different from this kind of standing wave. 它中间最重要就是这个最低点呢有没有掉到0 ？Okay. 那 if you have this point drop to 0, this means that you have 100% refraction. Okay, and gamma, the absolute value of gamma is going to be equal to 1. Okay, and if you have some value between this maxima and minima, then this means that you have partial refraction, 只反射过来这个部分的能量。那我们能不能定义一个参数来描述这个现象？也就是说，我们if we could establish some language that say some value, then you sort of understand that this is a partial refraction or 100% refraction. So people define a standing wave ratio like this. Okay, that is a ratio of the maximum value of voltage or current over the minimum value of a voltage or current. Okay, so if you have the 0 value for your minimum voltage or current, it turns out that this standing wave ratio becomes infinite. So whenever you see this S equal to infinite, it means that you have a perfect standing wave. Okay, you have a perfect standing wave if this standing wave ratio is infinite. Okay, if you have something in between, then the refraction is going to be partial. So I want to remind you this experiment. I did it for you, and so this experiment is in fact quite interesting. You can see a standing wave propagating on this line quite clearly, right? 我很喜欢这个实验，因为你真的可以看到这个 standing wave 就在这里做 propagation， right？ 这是一个前面是一个 node， 这里是个 node， 所以呢，你从这里到这里呢是2/2波长的长度。Okay, and if I swing faster and with the right frequency, 你看到其实我必须 swing with the right frequency, otherwise it's not going to oscillate. Vertical oscillation 你们比较容易看到，来，因为这个边界条件的关系，所以呢，我必须固定在某个频率，不然的话它不会震荡起来。你可以看得清楚吗？中间有一个 node 在那个地方 ，right？ 然后呢 ，if I swing a little bit fast, well, I guess I'm too old to do this, 或者是 too young to do this. 如果说我将来中风的话，我就会动得很快。Anyway, so you can see two nodes at the center, and 我不动它好，反而还比较快一点。我为了让你们看清楚，所以我的 vertical swing. But in fact, for me, it's much easier to do this. Okay, 你看到有两个 node 在那个地方。Basically, the standing wave ratio for this is 100% because you have a hard boundary over there. 你能量传不过去，碰到那一端之后，它全部反弹回来。但是呢，这是很糟糕的现象，因为你的 application 通常就是放在那个地方。你希望你手甩的这个能量呢，就是 you transmit your energy all the way to your device without any reflection. Okay, but this is just one, I would say, classic example that to show the 100% reflection of the wave. Okay, so you can play by yourself. Okay. So what actually I show you is sort of short circuit version of the transmission line, or open circuit version of the transmission line. To a string, the boundary is fixed without any freedom. So this is sort of open circuit, well, it's sort of open circuit to electric current. 因为 open circuit 对一个 electric current 来讲的话呢，电流必须是0，它动弹不得。OK， 或者是一个 short circuit to a voltage， 因为 short circuit 的话对电压来讲的话是动弹不得的。OK， 因为 short circuit 上头的电压就是0。那这个绳子基本上就是这个short circuit version for the voltage or open circuit version for the current. Okay, so for short circuit or open circuit, 你的 gamma is equal to 1. Standing wave ratio is infinite. This means that you have 100% reflection. Okay, well, 我们来看一下。Suppose that you have a resistive load. Okay. And on a lossless transmission line, your characteristic impedance now is equal to square root of L over C because R and G are equal to 0. Now, suppose we simplify the low impedance at the end of the line and make a resistive load right here. So you don't have any imaginary number. 你这里没有任何虚数部分在那个地方。Okay. So let's just sort of try to catch the concept. Well, if RL larger than R0, well, this is the open circuit or short circuit diagram for the signal on the line. So let me go back to this a little bit. 这个地方这个讯号变成0。相当于 you have an open circuit for the electric current. Yeah, you have open circuit for the electric current. Therefore, the current has to drop to 0 at the boundary. Or you have a short circuit for the voltage so that the voltage has to drop to 0. Okay. For this point, it's an open circuit voltage because for open circuit voltage, you have a maximum value, okay, or short circuit current, so you have maximum value of current right here. 所以呢，这个 standing wave 的这个 pattern 画出来的话 you need to have the ability to interpret the if this is going to be a current or voltage, and very often that if we know the voltage, we know the current because the current is equal to the voltage divided by the low impedance. OK， 所以呢，我们经常就是了解怎么去 interpret 这个图 in terms of voltage, and then it's good enough. OK. Now for resistive load, it's particularly simple because there's no complex number, 没有复数在里头了。所以呢，我们来看一下 ，if this low resistance is larger than the characteristic resistance, then gamma is a positive value. Okay, gamma is a positive value. This means that the refracted signal does not have a phase. Does not change the sign of the signal. 也就是说，你注意到这个反射的讯号 ，if this is a positive value, this means that the refractive voltage is going to add on the instant voltage, right? You have this gamma equal to V naught minus V naught plus. So the refractive voltage is equal to gamma multiplied with V naught plus. And the V total voltage at the low is equal to the sum of these two terms. So if gamma, so this is equal to V naught plus gamma V naught plus. So if this gamma is a positive value, then it means that the total voltage on the low is going to be the sum of these two. OK， 也就是反射的讯号呢，加上去你打进去的这个讯号。So in the end, if you sum them together, you are going to find that this point of the value is going to be the maximum. because the two terms add together. Okay. On the other hand, if your load resistance is less than the characteristic resistance, then you have a pi phase shift. This means that if you have a wave instant on this boundary, then the refracted wave is going to have a reverse phase. So positive value minus a value is subtract from your positive value, then you end up having a destructive interference. Therefore, the value is going to drop from a high value to a low value. Okay, 所以呢，你可以看到就是the reflection phase, in fact, will determine the value at the boundary. Okay, so if you have a short circuit, RL is going to be equal to 0. 所以对 voltage 来讲的话 because this reflection coefficient is defined through the ratio of the voltage. So if RL is equal to 0, the reflection coefficient is -1. This means that you put 1 volt in the forward direction at the boundary is going to refract -1 volt back. 然后1减到-1给你在这个边界上头一个0的值。Okay, if you have a short circuit. And of course, for a short circuit, the voltage is going to be equal to 0 at the boundary. Okay. 但是对电流来讲的话 if you have a short circuit, you have a maximum current at the boundary. Okay. Therefore, you have the maximum value for the current. This means that if you have a current pulse propagating to a short circuit ended transmission line, it's going to propagate back with the same phase, But if you have a voltage propagate over to a short circuit terminated transmission line, it's going to flip the phase and then propagate back. OK, 这样了解吗？因为边界条件的关系，所以这个反射的相位很重要。OK, and in fact, I'm going to show you one video to tell you a real experiment. Okay, so this is video time. I want to show you one video. 这是在 YouTube 上头拿下来的一个我觉得很好的一个 video, but in fact there's a little bit mistake in the interpretation. I hope that you can sort of catch it. So I want to show you this video. To do this, I think I need to take this, put it here. And then 我希望你能够听到它的解释。We'll see how good it will work. Oh, I did not log on. I did not turn on. 对于工程的人来讲的话，或应用物理的人来讲的话，你真的是要把一些观念真正的做出来，用实验做出来。所以我会很强调能够做一些实验给你看，或者是修一些实验给你看。All right, I think it's ready. Okay, listen carefully.
What we have here here is a signal generator sending out a square wave signal. And that square wave signal is being sent into the end of a long cable. This cable is all spooled up here. The end of the cable presently is open. I have one side of a potentiometer hooked up to it, but otherwise we'll have nothing. It's just an open connection. And then I'm also taking the oscilloscope and measuring the voltage signal at the entrance of the cable. If we take a look at it here, you'll notice here on the display, I see just a plain old square wave. Nothing special about that.
Square wave
goes down. What we see here is the signal of our frequency generator. I can change the frequency of that using a fine adjustment.
Change your frequency.
I can change the amplitude.
Okay.
And what we have here is just a plain looking square wave. Pretty boring until we begin to speed things up. I speed up my time base on the scope, so I'm looking at fewer cycles. And I will speed up the frequency on the signal generator. You'll notice we start to see little glitches here. In the rises and the falls, we see little dots where something else is happening. We'll speed this up again, higher frequency yet, and I will speed up the time base on the oscilloscope. And we see here what looks like a glitch before is actually a small step before the main step of the
is different from a square wave.
So we'll continue to increase frequency and see what happens.
So you continue to increase the frequency.
Get shorter and shorter pulses. And we notice that little step right there does not appear to change in width.
You see that this width actually fixed.
High frequency,
no matter how you change your
low frequency, that step does not change width. Even though, of course, the period of the square wave does change width because the frequency is
does not change.
Now
and that is something
interesting. So we get a more detailed look at that pulse. And we see once again, speeding it up and slowing it down, I have the same width.
You see the fixed width right here.
Led to wonder, where is that pulse coming from? Where's that step coming from?
That is actually the refraction from the end of the transmission line, because the transmission line length is fixed. Therefore, the propagation time for the signal to the end of the transmission line is reflected back.
During that time, that cable acts like a resistance. It acts like a constant load to the signal generator.
这里头已经有这个反射的讯号回来了。所以把这个 square wave 呢，叠加在这个反射回来的这个讯号上面。
We see the full open infinite impedance of the cable. When the pulse changes again, the cable momentarily acts like a load, which is why this square wave signal does not rise to its full amplitude immediately. It rises to roughly a half value, and then when the signal reflects all the way back, it steps up. I'm going to increase this one more time, get a more detailed look at this.
Okay, let me hold this for a moment. I want to tell you how you're going to interpret this diagram. So this is a transmission line all the way down, and this is sort of open circuit, all right? It's a transmission line. And for the first experiment, basically you have open circuit at the end, and the experimentalist is picking up signal at the beginning of the transmission line. And then it sends a square wave into the system, into this transmission line, and this is the zero value, v equal to 0. Okay. What happened is that once the signal is propagated to the end of the transmission line, the signal reflected back. So there's always some attenuation in the line. So the reflective signal is comes back like this. There's a time delay. Okay, there's a time delay. Therefore, the reflected signal is sort of shifted along this direction for some time, and then overlap with the original signal. So this is in this direction, and this is the y curve is in the forward direction. Okay, and then these two signals overlap each other. Okay, this is open circuit. Remember I told you that the refracted signal is in phase with the instant signal for open circuit voltage. Right? 对一个电压来讲的话 ，open circuit 的话，反射回来的这个讯号的相位是跟打过去的讯号的相位是一样的，所以你可以看到这里是正的，我这里还是画正的。OK， 了解吗？了解哈，反射回来的讯号它还是正的。So you overlap these two signals together and sum them together. So you end up having a signal added up. OK， 在这里呢，这里加这一段你整个加起来，碰到这里的时候呢 ，you have something negative, so you drop all the way down, and then come to this point, and then you add together like this. 然后呢，到这里的时候，这个负的跟这个正的相加，多出一点点正的，到这里，然后又上去了。这个橘色的线就是你在上头看到的这个线 ，OK， 从这个上去 ，and then you drop 0.9 is right here, 0.9 is somewhere in between right here， 有没有看出來 0.9 is right here, so you have some square wave goes up and then come back to below 0.9, right? You have some amplitude go up and come back down to somewhere below this 0.9, this flat part. 有没有看出来？我最好把这个 video email 给你们，然后呢，请你们写一个报告给我看。you need to sort of understand this, otherwise. Well, this is a real world example. 这个非常难得的一个这个实际的世界里头一个现象，你应该设法有兴趣去把它了解它。OK. So you see that the signal comes sum together and then give a value that is below the 0.9. 你的 0.9 在这个地方，这就是你的 0.9. OK. 所以呢，这个 step 是来自这个加上这个，你看。从这里到这里是负的，这里是正的，但是正的比负的还少，所以你就会加出一个负的值在这个地方。You got it, right? You do understand it, right? Okay, you do understand it. Good. So, but for this part, this is negative value. This is negative value. So you sum them together, you get something that is more negative. 更下来了，所以呢，就是这里从这里哇掉到这个下头来了。So this is summation of the positive signal and negative signal. In fact, it's an instant signal and refracted signal. Okay, for open circuit. But later on, this experimentalist, in fact, is going to give a short circuit example, and you can just follow this argument to understand the waveform. So I'm going to continue to play this for you. And this is a step that does not change width, because this is the time for the signal to reflect it back. Your 9 is fixed. Therefore, this is fixed. Now it's going to do short circuit example for you.
At first you might expect we get no voltage at all because we put it dead short on a 2-wire cable. But if we look over here at the oscilloscope display, we see we actually do have a signal. We'll slow this down.
Okay, so you have distorted signal because of the refraction of the line. Okay, I want to stop here. This width does not change because the refracted signal now overlap with the with the incident signal now overlap with the reflected signal with a 180-degree phase change, because now you have short circuit. 所以呢，反射回来的这个电压相位差了180度，所以呢，这时候呢，你把它翻过来之后，这个地方跟这个地方要相减 ，right？ 因为它相位反了180度，然后这里呢不变，所以你如果减下来之后呢，你会这里有一个凸出来的，然后呢这里掉下来，这里被吃掉，因为相减，这就是你看到的这个被吃掉的部分。Yeah, quite interesting, huh? And this width does not change because this width tells you the time required for the pulse to propagate to the end and reflect it back. 这是它跑过来又过去又回来的所需要的时间。所以呢，这里跟频率无关，它就是固定的一个时间。So let me continue this. So change the frequency, but the width stay constant.
All the way to the shorted termination, and then reflecting back as an inverted voltage pulse. So that
那相位改了180度 ，therefore you have a subtraction of the signal.
So once again, we see the width of that pulse right there remaining constant because it is a function of the cable
Yeah,
length.
the width is independent of the frequency.
Probably the most interesting thing that will happen is if we take away the short in the cable, we open it back up again.
Okay, now the experimentalist is going to put a low resistance to this line. Just use a potentiometer, variable resistor. So just connect it. 在这里 right here, he added a RL, a low resistance to this transmission line. So you can sort of tune the refraction, the amplitude of the refracted signal.
Now I have a potentiometer that I can adjust.
它是一个可变电阻，它开始改变的可变电阻，你发现这反射的这个量被改变了 ，because you have refraction coefficient equal to RL minus R0, RL plus R0. Now you are adjusting this, the low resistance. Therefore, the refraction coefficient change. 它那个 RL 是从0到一个 mega ohm， 所以几乎是从 short circuit 到 open circuit 都可以做到。你注意到它回到一个这个 square wave 的 ，because if you set this RL equal to R0, then this can go to 0 without any reflection. Therefore, you can turn the signal back to square wave. And this is called impedance matching. All right, if you adjust this to be equal. So there's no reflection. So what you send in is totally delivered to the low resistance, low resistor. And I think it's going to twist the variable resistor again, so you can see the change of the refraction. So we have to wait a little bit. Okay, it's varying this value again, so you can sort of see the refraction of the signal again. So if you can properly terminate the cable with some impedance, in fact, you can eliminate the refraction of the signal. Okay, so this is a very interesting and useful video. I just dig out in this afternoon. 有没有问题？看得懂吗？很好玩，对吧？这是 real time 的这个 play, and you can sort of really catch the concept. Now, occasionally, I think you want to log on the website, the course website, and I will update this set of PPT file. And below this video, I will put the website address for you. So if you are interested, you can just copy it and then view the video by yourself. Okay. 看了一些现象之后 once you have the concept, I think you still need to establish the ability to do analysis. Okay, so there will be some boring materials that you really have to go through by yourself and learn about it. Okay, power calculation is very important. 功率的这个计算很重要。为什么很重要？为什么功率计算很重要？因为算功率就是算钱，对不对？ Yeah. 所以呢 you need to know how to calculate the power. Well, you know the power is, from your circuit theory, you know the power is equal to the voltage multiplied with current. And both terms are a function of time. So any instantaneous power can be calculated by multiplying these two together. But sometimes you have positive value, you have negative value, because this is the AC kind of time harmonic signal. So let's just multiply them together. Okay. Suppose this is a time harmonic field, so you can use a cosine plus some arbitrary phase to represent this voltage and also to represent this current. So if we put these two together and use some trigonometry formula, you end up having this result. All right, multiplication of 2 cosine gives you the summation of 2 cosine. And the argument for this one is the subtraction of the phase. And the argument for this one is the addition of the phase. But this term, sometimes positive, sometimes negative. This means that you give the energy to some device, but you, sometime later you take it back. So actually you are not spending the energy. You are not spending the money, because if I give you the money and then later on I take it back, in fact, I have no loss, right? And what you really care is the net loss, net power, net energy I give it to you. So what we really care is this term. So this term is called the average power. Okay, it's called average power, because this is independent of time, and this term is something that give you a value, average value of 0. Okay, 你给的钱又拿回来, so you don't worry about this term, and so this term is the most important one that give you the average power you deliver to something. 那我们在之前的话呢说if we use the phasor to do calculation, we need to be careful when we deal with the multiplication of 2 complex numbers, because real part of phasor A and B is not going to be equal to the real part of A and real part of B. So if you want to do calculation for the power, you end up having, you have to consider this result. Okay, so we start from the calculation with the real number and real number, and then end up having a term that we actually care about. So we just need to find out a way to use a phasor to reach this expression. Okay, 因为我们喜欢用 phasor 做计算。How do we use phasor to do calculation and then end up having this expression? Well, if you see carefully, you can do this calculation to obtain these results. So if you want to calculate the average power by using phasor, then just use this formula. That will allow you to obtain the average power. OK， 所以这是在我们计算里头呢，我们有很多 complex number 基本上 phasor 的计算很容易很方便 ，OK。但是呢，你算 average power 的时候呢，我是不是可以用 phasor 下去算？答案是可以的 ，if you use this expression, OK， because this result is going to give you the same result right here, if you take a real part of it. OK， let me go through this very quickly for you. OK。So this voltage phasor is going to be equal to the voltage exponential j phi v plus, right? The current is equal to the magnitude of it multiplied with exponential j phi I plus. And then now let me follow this expression. The V plus I plus conjugate 1/2 is going to be equal to 1/2 V naught plus I naught plus exponential. Because of this conjugate, I will add a minus sign here because of this conjugation. Okay, so I end up having j phi v plus minus phi I plus. And then I need to take real part of it, get my answer. OK， 所以我把它取一个这个实数部分，这个实数部分complex exponential 实数部分 give you cosine, right? So this is easy. So you end up having 1/2 V naught plus I naught plus cosine phi v plus minus phi I plus. And this expression is the same as this expression. Okay, so this is the very a straightforward step for you to verify that indeed this is going to give you the right answer. Okay, so this is the general form, step for you to calculate the average power given a known voltage and also current. How do I calculate the power transmitting on a piece of line? 我让你们休息一下10分钟，好不好？然后我们再回来。